Thank you, Alan. Yeah, I think this is my seventh DKNOG, and I think I presented at all of them. Typically, I talk about routing security or very like detailed subjects around that topic. However, this will actually be completely different, and I guess to some extent be similar to what I did the first time I was here. So when I was the first DKNOG and talking, I talked about DWDM and network architecture, and finally I can speak about that again. Typically, it's a topic that my current company does not talk much about, but starting from this year, we will actually be a lot more open on what's under the hood of AWS. So my corporate title this week is Senior Infrastructure Business Developer. I think my team is called something in ways of global network connectivity and network development, but that kind of changes every week basically. But I'm a BGP and router guy. That is basically what I do, regardless of titles and those things. I just want to make sure that everyone understands the first 10 slides I didn't do myself. They are fairly polished. They are from reInvent, but they fit fairly well into this presentation, so I will skip them as fast as possible so we can go to the interesting bits that will come a little bit later. So when we talk about the evolution of the network infrastructure at AWS, we typically talk in 3 steps. So when we started, around 2006 was when we first launched the EC2, which is a virtual machine essentially. It was primarily used for Uncle Jeff to sell books. However, that use case has grown a lot since then, and now it's one of the largest cloud infrastructures in the world. But at 2006, we were a consumer of regular network hardware. Around 2010, which is 4 years after it was launched, we kind of realized that none of the things that is in the Cisco price list is actually usable for us anymore. And that's when we started to think a little bit outside the box. James Hamilton is one of our SVPs. He has made a lot of interesting blog posts over the years. I'm sure a lot of people have seen some of his old presentations on how to think outside the box. Regardless what you think of Amazon or not, I think James Hamilton is one of the brightest minds on this planet in terms of networking and how we can think about networking. So I would advise anyone to watch his stuff. He writes almost all of his things in a private manner, so he doesn't necessarily represent Amazon, but I guess at the end of the day, we pay his bills. So this is kind of where we started, right? So the consume phase. We bought, essentially you go to the Cisco or Juniper or Nokia website, you go to the product page and you sort by price, but in the wrong direction, so expensive first, and then you put a lot of them in add to cart, and then you buy them, and then you run out of hardware very, very fast, and also money. So we were using industry hardware and software, extremely basic automation, like back in the days, like screen scraping and these things. We typically pushed everything we could ever buy beyond design limitations. And basically everything was large chassis that had a backplate and a midplane. This is one of these polished pictures I didn't do myself, but this is how a chassis looks like internally. There is a lot of line cards that has one or many forwarding ASICs on them. They have a whole bunch of ports. They have a whole bunch of PSU and fans, and they are connected with a switch fabric in the back. And they typically have 2 or even more control plane and CPUs. Today, we have not a single of these devices in the Amazon network. We use single chip based platforms, typically in a 1RU fashion, where it has a single control plane and CPU, where it's a single forwarding ASICs, and it has a whole bunch of ports. And we construct the network outside the box instead of inside the box. Next phase would be the create phase, and this is basically around 2010, 2013 mind frame. It's like, what can we create with what's currently available in the market? I'm not sure if you have this book on your bedside table. I do not, because it has 2 problems. It is written by a French guy. Also, it is about telephony switches, right? However, Charles Closs is regardless of that, almost a genius. This is technology from I believe 1953 on how to build a non-blocking switching device for telephony systems. And this is today, I would dare to say that this is a standard design in essentially any data center you would ever have. So to make it super, super simple, a Closs fabric is a way of, for example, creating an 8-port switch out of 6 4-port devices. And this can obviously scale to almost indefinitely. most of the data centers you will see today is using the technology from this or a version of it. You have fat-free folded designs. You have 3-stage class, 5-stage class, whatever you have. They're virtually the same. They're working with the same principles. They were typically or are typically based on merchant silicon today, I would say. You can have internal software, and you can optimize the network design fairly well. And that's us, 2013, approximately. If you take this down even further, right? Like, what does a operating system? If we just look at the operating system, what is it? And this doesn't really matter if it's a white box, or if you buy something from a new cool startup, or if you buy something from a non-cool regular vendor, right? They basically work the same, right? Like, you have a network ASIC, you have an SDK in front of that ASIC to steer basic functions of that ASIC. You most likely have a Linux kernel, and I guess before you could also have BSD kernels, and then a whole bunch of stuff on top of this. And we wanted, and we're still in 2013, wanted to look at these things individually. Like, what could we do in each of these boxes? So we started out by the routing protocols. We have been running OSPF way above OSPF's limitation for 10 years. And the only reason why we could do this is because we wrote our own OSPF. That's really the only way we could scale. There was probably purists in here that was like, oh, why are you not running ISIS? Or why didn't you invent your own? Well, OSPF is actually a pretty good product. It's a great protocol. So building small things on top of that to make it optimized actually solves all of our problem and still does today. Same with BGP. BGP is the foundation of everything we build. Everything internally in our data center network and everywhere in between is using BGP and OSPF in combination. But we want to achieve, for example, super low latency connections. We want fast reconvergence. And given that we, at least today, control all of these boxes ourselves, we could actually achieve that with standard protocols, but with our own additions. So, create phase, what did we focus on? Config generation. Instead of having an engineer type in every single device like a bespoke thing, there was central config generation where essentially, oh, engineer, what are you going to do? It's like, I'm going to deploy a new cloud in Beirut. It's like, all right, here is that standard configuration, blah, blah, and here it is, done. Deployment coordination, like obviously we don't want to deploy things globally at the same time. That could potentially create a global outage. So we have release pipelines where maybe we don't do, for example, our cloud region in Ashburn at the same time as the one we do in Ohio, because they are typically redundant to each other. And then it comes to the next stage, like maybe this building and this building doesn't upgrade at the same time. Go one step below. Oh, maybe these pods in this building doesn't get upgraded by the same time as these ones gets upgraded. So it's like coordination in many, 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 many layers that eventually boils down to a deployment pipeline. Active telemetry is also something that we did back in the days, and still do today, obviously, where we actually try to understand what's happening in the network. Like, what are we actually seeing? We are using, obviously, NetFlow, SFlow, whatever it is, but also more things, like telemetry from the devices itself. Like, how is BGP feeling? How is OSPF feeling? Are we flapping? Do we have... looking at TCP window sizing is super interesting. Like, why doesn't BGP actually open large windows, for example? Auto-remediation is also interesting. It's something that solves roughly 95% of our problem, all the way from the data center, all the way out to the edge. Today, we are still NOC-less. We do not operate a traditional NOC. We obviously have people on call, but we don't have people that sit in front of big screens that look at alarms. We rather react on whatever the auto-remediation couldn't solve. So that's what we've been building our foundation on. And then comes the next part. And this is the interesting bits, because these are the slides I made myself. So, innovation. And this is, I would say, I think we started on this journey 2016, 17, where we were thinking, is like, what do we actually want? Like, if we think about networking long term, like, what is valuable to us? Freedom to examine trade-offs is, I guess, number one. It's one of our core tenets here for how do we design and build networking. Custom hardware was also very important. Seeing as we are, I guess not many people know this, but we actually bought, many years ago, a hardware vendor called Annapurna Labs. And they've been building most of our custom hardware for a long time. For example, they've been building our network cards for our servers for, I believe, 12 years. And they have expanded a lot, but they're only our vendor. So they have not been very good at marketing it. But here I am, marketing some of our own stuff. We have multi-domain applications. Today, AWS, the service catalog, I don't know, 300 services or so, I don't know, is a lot of them. So we want hardware that can that can serve, machine learning, high performance type of computer stuff, but also general computer stuff. And where I work, which is typically edge, peering, transit, backbone networking, we want things that could cover all of these things. And we don't think that is achievable without us having very, very flexible hardware. And also, we just focus on the benefit. We don't really care about anything else. We just want to see what can this box solve for us. So when it comes to innovation, this is, I guess, a fairly simple diagram that if you have low complexity and low innovation, you're fairly restricted in what you can do. High complexity can make you frustrated. I'm not sure if anyone been around back in the days in the OpenFlow days. I was a lot of complexity and for very little innovation, but the frustration level was really high. With high innovation and high complexity, you can quite easily get overwhelmed. And I think we've been in this box quite a lot. So something that we have been doing quite a lot is to reduce complexity. The simpler it gets, the better it gets. And that's almost a universal truth in anything in networking. So simplicity scales. I didn't do this slide and did it myself. This is a marketing slide, but whatever. But technical depth. I think everyone in here can agree that technical depth is not fun. And that is one of probably a core problem for everyone in day-to-day operations, that you regret your decisions 10 years ago. And obviously in 10 years, we will be there again. Then we be here and regretting the things that I will do tomorrow, right? So to avoid that, always think in terms of simplicity. And I will show you how we do that. One of the things that we started to do was to have one device for everything. And this is actually our device. So it's green. It is a type of white box, but it's actually green. It's, as you can, so you can actually go back. So it is designed by us. The red card you see up there is the CPU. It's our own stuff as well. So it's a Graviton-based controller. So it's an ARM-based CPU. It's the same thing as we run in our ARM-based instances in EC2. It's using our own custom front plate. Yeah, the whole device is our own design. It's using a 12.8 terabit chipset as a networking ASIC. It is multi-sourced, so we can buy it from multiple places, and we can pit these vendors against each other, which is also very important to get the right bang for the buck. So this device is, I wouldn't say 100% of our network, but it's at some point it will be. We've been using this type of device for many generations inside the data center, but it's moving out. So it is coming all the way to the edge network. So unfortunately today there is no one in Copenhagen that pairs with this box, but I believe the first one will be Global Connect very soon. That will be on a 400 gig peering inside this green little box. So inside of this box there is obviously a networking ASIC. It's a single one. It's multi-sourced, so we use different vendors, but they have the same type of port density or port speeds. And in this case, it will be 32 by 400 gig for this generation. We put out vendors to silicon vendors, so you have Broadcom and you have a couple of others that can just answer our tenders, and we buy chips from them, and hopefully it's all of them. We control the CPU. It's our own little server, so it's the Graviton one. I would say that we have typically put in a much beefier CPU than what most people do, because we would like to offload most of the network functions to this device and not run it somewhere else. So the only thing now, I mean basically in planning and acquisition, right? So I decide where the network goes in the world. So whenever I go into my order system, nowadays I only have a single thing I can order. Actually I have two, but this is our typical 102.8 terabit router. This is what we deploy, has been deploying for the last 2 years, basically everywhere. So it's 16 leaf devices and 16 spine devices, although we don't call them like that, but that's essentially what it is. They are connected together in a non-blocking fashion, of course. And what we end up with is 256 400 gig ports for consumers. So consumers in our world, given that we operate the AS16509 network essentially as an ISP. So my consumers or my customers are everyone. It is my peers, it is my transits, it is backbone, it is, of course, internal customers such as the CDN, such as the cloud, machine learning services, whatever it is. Anyone that wants to use 16509 network for something are my customers. So if we have a lot of CDN on a site, you know, they will consume a lot of ports. There will be a little bit less of peering, and we obviously have an idea of balance here. Before we had this idea, we had a box that had any function, you know, or sorry, that had a specific function. So we had a specific core router, we had a specific PE router, we had a specific aggregation router, a CDN router, a management router, a blah 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 router, you know, a lot of discrete components where we had to right size it every time. It was like, oh, how much backbone do we need on this site for the next 5 years? It's like maybe 7. And then we figured out how many boxes that would be. And we were almost always wrong. So we ended up having to go back. And it's like, oh, we needed more backbone or less backbone or more CDN or more peering or less transit, you know. And it was not very flexible. We had to do a lot of rack and stack and lift in a lot of boxes all the time. With this new idea, which internally is called basically a universal fabric, you know, we can just shift it by changing name on the port. And it's like, oh, now this is a backbone port. Now this is something else. And that's where we wanted to end up with. So, as you can see here from the slide, this is a 30 kVA rack. For the ones that have been acquiring colocation, it's not very easy to get this type of rack. I wouldn't say public colo very rarely offers this. There is a couple of new players on the market that actually has these capabilities because you typically need in-rack cooling in these things. But our version of that is, this is the same router. This is also a 102.8 terabit router, but we spread it out over 4 racks, and then we can fit in typical general public colo, which is great because we also want to be where the customers are or the consumers are, so that we can connect with them. So this is virtually the same. And of course, we have an out-of-band switch and a management switch inside the rack. And every time we want to scale this out, you know, it scales almost indefinitely. So if we go to 4 racks, we build them separately, right? Like we convert some to pure spine racks, and the bricks, they have all the consumer-facing ports. So this would be a 204 terabit router. And we go today all the way up to 3.2 petabits, which is for us 32 racks. If we only have 10 kVA racks available, that would be a lot more racks. It's 32 times 4 racks. But a site as large as this, then we're not in public colo anymore. Then it's another type of site. So we can actually do 32 kVA racks. So that's how we design the network today in terms of scalability. And the next generation would probably be a 25.6 terabit chip or something like that. So like the building blocks are actually the same, but there will be increased port speeds. So another cool thing, or maybe not cool thing, but how do we do it inside a rack? So DAC cabling is something we've been using quite a lot, and I think most of you has been using DAC cables as well. One of the massive problems with DAC cabling today is the outer diameter. When we cabled our first devices with regular 400 gig DAC cables, there was no airflow at all because the cables just eat up the whole faceplate. Like there is no air left. So that's our biggest enemy, right? The cable diameter. So we've been working a lot with our vendors and partners in the industry to do DACs with active retimers. And this reduced the cable area by about 50%. And that actually enabled airflow in front of the device. For short reach things, so the little rack there to the right is a cabling rack for 4 routers. So or rather 4 of these racks. So every 5th rack essentially is we had to install one of these just for breakouts. Because on the 100 gig era, we relied a lot on the breakout optics. And this causes a lot of problems because we consume every 5 rack just for cabling. And if you pay Equinix that amount of money, you're not a very happy company, right? For a passive rack. So to solve this, we work with a company called Senko to create something called an SN connector that does breakout directly inside the optics. So the thing you see there to the right, yes, that's right, yes. It's a 400 gig DR4 Plus with an SN connector, where it does break out to 100 gig, because obviously, even if our networking device are 400 gig, most of the consumers of the network are still on 100 gig. So we break it out with a 400 gig DR4 Plus optic, where we don't need external cabling racks. We can connect directly with the fiber cables to the optics. And these are not as cumbersome to use as you would imagine. You don't need like tools or anything. You can actually just use your fingers. There was another standard, I can't remember the name, but it required you to have a fairly advanced tool to get the actual connectors out. And this technology is not only for Amazon. Like, you can buy it from probably any vendor fairly soon with the Senko connector, SN connector. So we're quite happy with this. This is the largest building block inside the whole Amazon network, and we consume these in the hundreds of thousands. So this is, yeah, our main component. Okay, so short-haul DWDM, sometimes called data center interconnect DCI. Contrary to popular belief, this device is purple, but it's not from a vendor that typically does purple devices. It's our own design. And it's relying on the 400 gig ZR technology. I'm sure there will be another talk about that today, or maybe tomorrow. We use this for anything that's sub 400 kilometers. It has integrated routing, and it has DWDM and encryption in this case obviously means MACsec. Because every time we leave a building, we have MACsec on the link. Like, internally inside our building, where we consider them to be a red zone, we don't need encryption, but as soon as you will leave a red zone, which is a cage or a building, it's going to have MACsec on it. That's a promise we have to the customers, so that's what we do. And this device fits together with these green devices. This is my only other thing I can order in my internal ordering system. So I could order that 102.8 terabit router, or I can order this, which is Metro DWDM. And it has 8 of these switches, and in the middle it has 8 of these DWDM switches. The reason why there are 2U is fairly simple. There is not enough cooling capabilities in a 1RU device, so it's a 2RU device. And hopefully in the next picture you can see that the cooling intake by the optics are fairly big. So to the right, you will see this super fat DAC cables that goes out to the leaf switches. So this is essentially, like, this whole rack is a DWDM leaf. And all to the left, we would put in the 400 gig ZR optics. And this is what we will do if we, for example, inside a city or with cities with very short distance, we can have these face each other. Unfortunately, this type of innovation has not come to long-haul DWDM yet, but I can guarantee you that we have a fairly big team that is looking at that as well, on how we can bring simplicity to long-haul DWDM. Because if you work with long-haul DWDM, you know that it is very far from simple, and you need a billion fucking SKUs to produce a DWDM node that shoots a far distance. But we think that is not necessary in the future. But for now, we still need to rely on these big service catalogs to be able to produce long-haul DWDM. So we have a small number of rack variations. We have rack cable switches for burning, which means that we actually cable the racks at our factories before we send them out. So whenever engineers come to the site, it's already built. They just need to roll it in and connect external stuff, and then it's ready to go. We also do a fairly cool system, which I was exposed to first time for 2 years ago, that we essentially use barcode scanners to make sure that everything that was ordered is actually there. So the first thing that happens when one of these racks arrives to a site, the engineer will take a regular barcode scanner from like Netto and like beep, 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 shoot all the devices, make sure that it was the right devices and that everything is there, and then release the rack for production. So I have about 5 minutes left, I believe. This is a picture I made myself, and that explains how does the software work in this type of site. So I will walk you through it. So when you peer with us today with a 400 gig, or at least in our 400 gig platform, which in Copenhagen is no one for now, but very soon it will be. Hopefully I have that site ready in like a month or so. you will actually not peer with a router. You will peer with a container inside a little local cloud that will run on the side. And this is being done in a very, explained in a very simple way. They will essentially grab the BGP signaling traffic from the link, encapsulate it, send it into the container, and that's what you peer with. Today is a mix in that container. Sometimes you peer with externally supplied software, and sometimes you peer with internally supplied software, a little bit depending on requirements and what you are. If you are an IX, for an IX, it would be externally supplied software, and if you're just a regular PNI, will probably be our own software. Because we are still a little bit afraid of the scaling issues that we have with our own software, so we want to take it slow and steady. This container would of course only have that single the route view for that peer. So it needs to spread it to a route reflector. So in this case, I had an example how it could look like in Copenhagen. So Copenhagen has a view of everything Copenhagen, because we would have 16 leaf routers and I don't know, 100 peers. So we need to collect all that data into a single route reflector. We do the traffic analysis, we do traffic engineering, we do RPKI, routing security, filtering, blah, 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 everything like that over there. We send all of this to what we call a road programmer that takes a lot of internal business intelligence or technical intelligence, both from NetFlow or from TE. We have a whole bunch of different TE systems that looks at the traffic. It's like, should I do something else? Should maybe perhaps this traffic be in Hamburg instead of in Berlin, etc. We have overrides, and we have CDN data, which is a mix of GeoIP and user data from clients. And we try to figure out what would be the right way to actually program this route. Because the thing is, our devices cannot take full tables. So we need to be selective how much routes we fill into the fib of these devices. So we have something called hot routes, where every single metro has their own view of what hot routes are. Our goal is to achieve 99% plus of hot routes that is locally programmed. And so far we built about 100 metros like this. And so far we have achieved 99% on all of them. For the 0.1% that is not a hot route, we actually do have our very regular full table router that sits on a stick in the back. So it consumes essentially a consumer port. And even for a very, very, very large site, we could just do that with a single 100 gig to that router that's on a stick. And then, of course, we will tunnel everything back and out to the consumer, which is people in this room or internal services that is using the same system. I believe I have about 1 minute left, which is perfect timing because this is my last slide. The red dots are where we are going to build this stuff. The yellow dots are the ones that are finished. We hopefully have about 400 or so of these sites by the end of next year. And when we're done with that, I guess we need to start migrating to the 800 gig again, right? So it's like a never-ending circle of things you need to do. That's everything from me. Thank you very much.
Thank you very much. We have time for one question or one or two.
Tom, Cloudflare, you mentioned that you put out a tender for silicon vendors to give you silicon that doesn't suck.
Correct.
The problem that we're encountering with this is that the SDK on top of it sucks.
Yep.
Is that something that you're actively pushing your vendors towards more a system like B4? I know I'm making, Aaron isn't here, so I need to do the B4 talk. So is that something that you're actively pushing for, or do you currently still have software developers that just need to deal with like the gazillion different SDKs and then just integrate it for yourself, or?
Yeah, I think unfortunately, I can't write an NDA with the whole public here, so I couldn't be able to answer that question. But surely there's a lot of interesting innovation in specifically the SDK there, because today that's a $10 billion market to protect. So to challenge that is not an easy feat, but surely it's very interesting.
Hi, Rory from Google. Nobody gets fired for buying Cisco. Will I be buying from Uncle Jeff anytime soon?
Well, unfortunately, as far as I know, we do not have any intention of basically making this a purchasable product. Maybe that changes soon, I don't know. Jeff bought a new boat, so maybe he needs more money, I don't know. But I wouldn't think that, but rather the idea, right? That obviously not everyone can go out and build this super complex. Well, they're not complex; they are simple, but it was a lot of complexity getting there. So we'll see, I guess. But hopefully, the industry in general can focus on core values and simplicity.
We'll take one final question.
So basically, you
Who are
said
you?
that I'm Alexei from Finland, Axel. Hi.
Kiitos.
So you said that the brick node basically has its own little cloud that does the processing, and that raises a question: how long does the bootstrap process of a brick node take?
A bootstrap?
How long until, if you power it on, how long until it's actually going full speed?
Roughly a minute. The devices are super, super quick to boot because they have very, very few protocols. Like, if I go back, I can't go back, whatever. So these devices, right? Like, you could look at them as a Linux computer, right? We essentially have our internal packet manager where you install things such as LACP, or you can install ARP, and you can install these things. And these devices have like less than 10 packages on them because we typically do LACP, ARP, IP and IP tunneling, and like 5 more things. Like they do not have any other processes installed. So they do not have like multicast installed. They don't have protocols you don't need installed. So all of these things are ripped out. So it's a fairly specialized computer that's also a switch. Alexei has a follow-up.
But what about having the full routing table or whatever the hot portion is?
Well, full convergence obviously takes a bit longer, given that we also have a whole set of route reflectors behind it. It takes, I don't have a good number for you. It depends a little bit on the site. Like a couple of sites are really big. That's like, 150 route reflectors in tandem working. That's a couple of minutes of total convergence. But smaller sites such as Copenhagen, I would imagine like 5 to 6 minutes before all the route reflectors converge. Because also they are our own BGP software, right? So they are very optimized for our use case. I think we're out of time, right?
Yes, we are out of time. Thank you very, very much, Fredrik.
Choklad! Tack.